Hi, my name's Andrew Sorensen and I'm absolutely delighted to be able to speak to you today at the European Lisp Symposium. I've been a Lisp programmer for many years and also a Lisp implementer, although my Lisps are sort of a bit unusual for a standard Lisp, as you're about to find out today. I've taken this opportunity today, COVID and all, and because of the format we're working under and that I can't be with you physically, to present more video material than I usually would. But I'm hoping that this video material helps to convey this broader theme that I'm talking about today, which is this idea of cyber-physical programming, which is loosely speaking the idea that a programmer can be embedded within a real-time system and that their programming through the programming language interface can be an activity that happens in real time, affecting the world in real time. The programmer then becomes a sort of an embodied part of the cyber-physical system, and this interrelationship between the programmer, the machine and the environment is one that I find really quite fascinating. Anyway, I'll come back and talk to you again at the end of the film, but I hope you enjoy the next 35-40 minutes or so. Cheers. This is extempore. And this is a style of programming that I call cyber-physical programming. Which is a rather pretentious sounding term for an exploratory style of programming that Lisp programmers have been exploring for more than half a century. In this particular instance, the cyber-physical programming is a musical concert where I'm programming a robotic piano live in front of the audience with the screen projected above so that they can follow along with all of the code as I build the piece that they're listening to. In this particular instance, listening is important because the programmer is part of the cyber-physical system, part of the environment. But before we get into cyber-physical programming, let me just back up a bit and let's have a look at what extempore is first. So the first thing that we have to say about extempore is that it's actually made up of two different languages. It's made up of Scheme, and R5RS to be specific, and a new language specifically designed for extempore called XTlang. And in this top case we have the GCD function written in Scheme, and below we have the equivalent written in XTlang. In extempore, these two languages are designed to interoperate. Scheme is callable from XTlang and XTlang is callable from Scheme. In extempore, Scheme language code is always interpreted and XTlang is compiled to native code. As a language, XTlang has a number of properties that make it quite unusual as a Lisp. The first of these properties is that XTlang is a statically typed language. In this particular case, the GCD function has been compiled to a function taking two 64-bit arguments and returning a 64-bit value, as can be seen in the log. XTlang supports a type inference system, and in this case the 64-bit integers have been inferred because of the 0 literal in the equals expression. This is all that XTlang needs in this case to infer the rest of the types for the function. Explicit types can be provided to provide hints for and to override the default behavior of XTlang's type inferencing system. XTlang has a polymorphic type system. We now have GCD functions in i32 and i64 variants, which in this case results in an ambiguous call to GCD. This can be resolved by providing some additional type annotations. The i64 case and the i32 case. XTlang supports generics, and now we're going to create a generic GCD function with an A type variable. In this case, the A can be of any type, but the A's must match. We further constrain the A by making sure that it is a number, and this provides type constraints for the GCD function, ensuring that the type can be any type so long as it is a number. Extempore's constraint system is quite flexible and even supports basic dependent types. Here we try with doubles, which works fine. Doubles are a number. Another unusual property of Extempore's XTlang is that XTlang never boxes types. If the Extempore XTlang type system passes and allows compilation, you can be guaranteed that you'll get a fully specialized native compilation. This is important for the kind of systems level programming that we like to do with Extempore. Let's try doubles, i64s and i32s all together. Now let's look at a fail case. Let's look at a case where the constraint system catches an invalid type. Types that are not numbers will of course be rejected by the constraint system, which is explicitly looking for types of number. Strings are not numbers. Let's bring a few of these ideas together quickly by working through the expression problem. Just as Extempore supports generic functions, Extempore also supports generic types. Here we are defining a generic literal type, a tuple of one generic element. The evaluation function here simply returns the first element of the tuple. Note that the type signature of a val has the return type first, followed by any arguments. So in this case, the return type A is the type variable, followed by the literal type, which is the first argument. The new add type actually allows us to add two different types, potentially, because the type variables A and B are distinct. Next we add two integer literals, and for a second expression we add three double literals and print the result of those expressions. We continue on by adding a subtype, including its evaluations. And we alter the expression problem to make the second expression use the subtype. Now let's add a stringify for pretty printing. And finally, we use the stringify to pretty print the two expressions in our primary expression problem, E1 and E2. So to finish up on extemporary's type system, let's have a look at one way that we could go about implementing a list in extemporary. At the top of this file, we see an example of extemporary sum types, in this instance named list. We then evaluate a series of monadic functions and standard list operating functions before finishing with a few simple test cases. Finishing with a simple pair and an example of a simple do notation. Another unusual property of XTlang, at least as far as being a Lisp variant language, is that it is not a garbage collected language. It is actually an unmanaged language. Extemporary makes use of zone-based memory, also often known as arena or region-based memory management. In this case, test 1 allocates 4 doubles for a total of 32 bytes of memory allocated into the memory zone, which we can see in the log below. Memory zones in extemporary are usually managed automatically, but can be manually controlled by the programmer, as in this example, where a new zone is pushed before the call to test and then popped after the call to test. Lexical memory zones commonly use a begin Z abstraction for this kind of behavior. In general use, most extemporary users don't have to worry about explicit memory management or memory zones, but when you need it, you need it. XTlang's unusual set of properties, including its static type system, manual memory management, and guarantee of fully specialized native code generation, make it well suited for doing many real-time systems and low-level systems tasks. This is a brief example using XTlang to build a low-level DSP signal chain in real time on the fly. Here we program a white noise generator and 2 oscillators, one at 220 Hz and one at 330 Hz. The gain of the oscillators is of course trivially controlled. Silence is of course 0 and just highlights the fact that this SND function that we see here is actually the audio sync. This is actually the function being called back by the audio device itself, which in this case is operating at 44,100 samples per second times 2 channels in this particular case. We now set up a simple delay line and we have a filter for the delay line, and this is all to set up a very simple coupless strong algorithm, which is a plucked string model, which you will hear in just a second. Calling init line simply fills the delay line with random samples, which are then filtered using the very simple filter over time, and this is in fact what gives us the plucked string. We can then actually pitch the plucked string by simply changing the duration of the delay line. It's worth noting how we can play the play string function in this case with fairly immediate response from the system. We then write a little delay function, an actual stereo delay, a ping-pong delay, and we add a little sequencing routine so that we can play a little melody by randomly selecting pitches from a pitch set. We then start working on a little FM synthesizer to join our pluck string algorithm. Really, the main purpose of this example is to demonstrate XT-Lang working from the systems layer without any underlying abstractions. There really isn't much below this apart from a thin OS hardware abstraction layer and the audio device itself. This is clearly a simple contrived example, and Extempore's built-in audio-digital signal processing chain is obviously much more sophisticated in practice. But this hopefully should give you a bit of an idea of the kind of low-level systems programming that Extempore has been designed for. Extempore supports a strong temporal semantics, and a common use pattern in Extempore is a design pattern called a temporal recursion. This design pattern works by allowing a function to recursively schedule itself for some future execution point. This turns out to be a very flexible pattern and is used extensively in Extempore programming. The following example is an old demonstrator I put together which shows temporal recursions with a graphical user interface overlay. Here you can see the first temporal recursion is defined as tr1, the function tr1, with a callback to tr1 being scheduled into the future. Once we call the function, you can see now there's a little graphical overlay with this circle printing around, showing a clock essentially to describe the scheduling rate. This is an example of modifying the code on the fly. You can see we were changing the pitches before. We're about to start tr2 now. tr2 is running at 3 times the rate that tr1 is running at, but again uses the same temporal recursion callback. And of course this provides us with a form of concurrency with these two running at the same time, but at obviously different rates. Here again just showing modifying this on the fly, changing the pitch as we go. tr3 is a third temporal recursion which will also run concurrently. This example is a little different because the callback rate is changed, showing that it doesn't have to be just a consistent rate, but the rate can be changed dynamically. Here you can see the rate is actually the list, so it's 4 beats followed by 3 beats followed by 1 beat and then repeating 4, 3, 1, 4, 3, 1, etc., etc. This is really just showing some heuristic techniques for live coding situations where you want to catch errors. You can see we add a bad symbol here. This heuristically gets picked up and modified to put a 0 for silence so it doesn't otherwise break into a debug loop or otherwise stop the temporal recursion from operating, which of course in live performance is obviously a very useful ability. A temporal recursion can be stopped in a cheaty way by defining the temporal recursion to be essentially a null function, which then stops or terminates the function. Of course, this isn't a very elegant way of stopping a temporal recursion, but of course it's a very fast and convenient way of stopping a temporal recursion in a live situation where speed is of the essence. These temporal recursions are all driven together. We can change the tempo of the whole lot, and we can see that the scheduling rate then changes for all of these temporal recursions at the same time. Although this is clearly a musical case where we're playing with it here, this kind of temporal recursion pattern is an extremely useful scheduling pattern for any kind of computation, and we use it extensively in Extempore. The next example will show a case where we use temporal recursions all the time. Extempore is well known as a language environment for sound and music production. But in fact, most of Extempore's original design and implementation was to support the QUT Cube Physics Playroom project. The Physics Playroom is a collaborative space designed to appear as a single unified scene, Human interactions in the space are designed to encourage cooperation by being inherently interconnected. A user can throw a block into another person's building, or even though they are working at completely different ends of the distributed display wall. The same general idea of interconnectedness pervades the playroom and makes the physics playroom a coordinated as well as distributed environment. The playroom is actually displayed across 12 55-inch multi-touch screens configured in a permanently mounted wall display. Additionally, a stitched projection runs across the entire length of the 12-panel display, effectively doubling the physical height of the wall. The physical dimensions of the entire wall are approximately 17 metres wide by 3 metres high, and the pixel resolution is combined at 12,960 pixels by 3,000 pixels. To drive this, the 12 multi-touch panels and 3 stitched projectors run in high definition 1080p, and in order to render the high pixel density of the wall is comprised of 7 render nodes. One render node per 2 touch displays, with a final render node assigned to all 3 projectors. These 7 render nodes are not only responsible for rendering the unified scene, but also for managing any other computational heavy lifting that may be required. For the playroom, these additional computational requirements are substantial. End-user interaction, dynamic scene, graph management, time synchronization, physics simulation. This was a classical mechanical and both classical mechanics and fluid dynamics, and of course audio signal processing. The physics playroom was written entirely in extempore, and in fact most of the development was done in a highly interactive cyber-physical way. Very often I was programming on a laptop with people actually interacting on the wall without even realizing that the wall was being written and modified while they were playing with it. This proved to be a really great development model actually, with very fast turnaround. There were lots of interesting technical challenges on the project. Here's a video showing a really early example of distributed rendering and the challenges of keeping the distributed rendering machine synchronized. In this case, there's 1 machine for the projection and 2 machines for the 4 screens down the bottom. Distributed classical mechanics was also an interesting problem. In this case, there's 1 machine rendering the 2 touchscreens on the right hand side, and a completely different machine rendering the 2 touchscreens on the left hand side. And of course we need to make sure that we keep the physics simulation that we're using here synchronized between these 2 machines. It was also really important to keep really high frame rates. We really wanted a really silky smooth feel to the thing. Of course, it's, when you have very high frame rate, it makes it easier to believe that these blocks are real blocks that you're playing with, and of course that's really important to a great user experience. Here you can see this, it's working really seamlessly between the machine on the right and the left, maintaining the state of the classical mechanical model. It was also really important that the system cope with large numbers of touch events, as we were expecting this to be, very interactive and multi-user experience. With, particularly it was targeted at school children, and so we had groups of school children coming through with, up to 50 or 60 school kids, of course, with 10 fingers each, all hitting the screens at the same time. So being able to cope with a large number of touch events was also an important part of the specification for the system. Again, this is another great example of where low-level performance really is super important. We also worked on a number of fluid dynamics simulations during the Playroom project. These were purely for graphical purposes during this project, but as chance would have it, we actually came back and started working with the high-performance computing team to develop particle in cell simulations and explore their interactive potential. Another interesting application domain for extempore is high-performance computing. In this instance, experimenting with particle in cell simulations. Particle in cell simulation, or PIC, is a common modelling technique used in plasma physics and engineering. A PIC code can be roughly broken down into sort of three main phases: a deposit phase, where the charge of local particles is deposited into a grid; a solve phase, where the electromagnetic field equations are solved to obtain an up-to-date field; and the push phase, which uses the newly calculated field to push the particles. Maximising the fidelity of scientific models while minimising the cost of their execution on large supercomputers is one of the central concerns of high-performance computing. Where C++ and Fortran, for example, are de facto standards for this type of work, a situation that has remained virtually unchanged for 40 years or so. And yet, while there has been little change in the development of high-performance computing codes for scientific modelling, there has been a considerable shift in the scientific community towards dynamic languages. Libraries such as NumPy and SciPy provide good numerical performance by hiding C code behind a Python veneer. Unfortunately, in practice, the relatively good numerical performance provided by libraries like NumPy is lost when code tends to bubble up into the Python wrapper. Ideally, we would like to be able to match the convenience of Python with the performance of C, such that the performance impact of bubbling up would be mitigated. In this ideal, the programmer could replace scientific C or Fortran codes in an interactive and opportunistic manner, sort of slowly cannibalizing extant scientific codes from the inside out. This is where extempore comes to the fore, as it can be used to cannibalize extant C particle and cell simulation code in order to facilitate free and fluid steering, tuning, diagnostics, and other important scientific discovery. In this case, we demonstrate extempore supporting bubble-up semantics, a desired property for any cyber-physical programming system, without sacrificing performance or the flexibility inherent in the original underlying C code. Extempore makes it possible for computational scientists to dive into sections of the code base as determined as interest arise, and make direct modifications to the running system on the fly. Furthermore, these modifications can be made to a single node or simultaneously across a cluster of nodes at the programmer's discretion. The cluster can be homogeneous or heterogeneous too, with respect to both operating system and CPU architecture, to the extent that extempore supports Linux, Windows, Mac OS operating systems. Another interesting cyber-physical application of extempore, although with a much slower turnaround time, is a robotic telescope application. In this particular case, we can see that the programmer has chosen to unpark the telescope, place a filter, then set a focus position. Then the telescope has been moved to point to a position in the sky, an image has been captured, and then the image has been checked and it's proven to be out of focus. So a change in focus position has been made, another image captured, and the important thing here to recognize is that the programmer is then identifying these things. The programmer is an interactive part of this loop. And the REPL is then providing a way or a means by which the programmer can interact with the telescope. Of course, larger scripts can be written, and a complete night's session can be programmed into the computer with potentially a number of targets, in this case choosing from a database of selected targets. We can see here also that different filters are being applied to each set of images being captured, etc. This is a slower rate of cyber-physical interaction with the system, but it is still a very integrated interaction, as in the programmer is still an integral part of this cyber loop. The term cyber-physical programming defines a live programming practice where the target domain is a cyber-physical system. A premise of this thesis is that there are domains for which the addition of a human agent, the programmer, is either necessary or highly advantageous for some success in a particular task domain. Cyber-physical programming provides a model for human supervised systems. Cyber-physical programming diverges from fully autonomous systems by integrating a human programmer in the loop. Cyber-physical programming also diverges from most semi-autonomous systems by shifting the focus of human interaction away from direct manipulation and towards meta-information processing. the desired, the directed orchestration and ongoing maintenance of many concurrent information processing sources. From an information perspective, the cyber-physical programmer fulfills a meta role, selectively influencing a continuous stream of real-time information. This information is sieved through the system by the careful manipulation of higher-level processes. The cyber-physical programmer does not directly manipulate the flow of information, but instead programs a network of cyber-physical agents to intervene on the programmer's behalf. This places the programmer both within the loop, but also above the loop. While the cyber programmer's role is usually second order, it's not strictly second order. The human agent may also provide a primary duty as an additional and far more complex sensory organ and information analyzer, an active and direct participant in the behaviour of the system. What cyber-physical programming attempts to provide is a balance between automation and control from a human perspective. What distinguishes cyber-physical programming from a more traditional programming practice are the real-time constraints imposed by the cyber-physical system being developed or controlled. These real-time constraints affect the overall performance of both the programmer and the underlying cyber-physical system. By making software development a real-time activity, software itself must become runtime malleable. It must become amenable to change in real time at runtime. As cyber-physical programming targets the building as well as the orchestration of cyber-physical systems, the tools of the cyber-physical programmer must adequately address 5 key concerns for cyber-physical systems. These include being reactive, where a reactive system's interaction with its environment is ongoing, where a classical computation's correctness can be captured with a mathematical function mapping inputs to outputs. A reactive system's correctness is naturally described by a sequence of observed inputs and outputs and their correspondence to acceptable behaviours. Concurrent computation involves multiple parallel processes of execution, communication, information in the service of a coordinated goal. For sequential computation, the Turing machine provides a canonical model of computation. No such agreed formal model exists for concurrent computation. Instead, there are many competing formal models for concurrent computation. Broadly, these can be broken down into synchronous and asynchronous models. Cyber-physical systems make extensive use of both synchronous and asynchronous models. Feedback. A control system interacts with the physical environment via a feedback from sensor readings to actuator adjustments, and round again in a continuous feedback loop. Control systems and their integration with discrete digital computing systems are one central concern of cyber-physical systems. Real-time. Programming languages and the supporting infrastructure of operating systems and processor architectures typically do not support an explicit notion of real-time, and yet a notion of continuous real-time is required to support the control systems central to cyber-physical systems. This is a challenging set of requirements for both software developers and programming language designers. Reactive programming, concurrent programming, real-time programming, embedded systems programming. On top of this set of programming requirements, the underlying motivation is to know whether it is feasible not only simply to program the cyber-physical systems, but more radically to live program these cyber-physical systems, creating cyber-physical systems that intrinsically incorporate a human programmer within the loop. Music is a form of cyber-physical programming that is highly concurrent, reactive, real-time, and involves significant feedback between the programmer and the sonic environment. Whilst musical live coding may be considered to be cyber-physical in nature, the term cyber-physical programming is more specifically used in relation to not only the orchestration of audio signal processing systems on the fly, but also to the building and or modification of the audio signal processing systems themselves live on the fly. In other words, the programming of the digital signal processing system, as well as its control of the orchestration or note layer. Live coding converges with cyber-physical programming with the target of the on-the-fly development is an audio signal processing system, a firm real-time system. Although live coding systems are not hard real-time systems, a failure to meet all scheduled deadlines during a musical live coding concert in front of a live audience is extremely detrimental to the overall performance and highly embarrassing for the performer. In extreme cases, such as high decibel concerts, it is even possible to cause audience members physical or oral damage. Missed deadlines in the underlying audio streams measured in microseconds represent a failure of the system, not simply a quality of service issue. Time then becomes a correctness issue rather than simply a quality of service issue for live coding musical systems. A core concern for cyberphysical programming and live musical practice is the programmer's ability to orchestrate a concurrent set of ongoing cyberphysical processes through the writing, editing, and execution of a program's source code. The programmer builds and modifies the behaviour of computational processes within the temporal bounds of the performance, within the temporal bounds of the task domain, that is. Success is predicated on the programmer's ability to build, execute, and modify these processes in a timely manner. For a musical concert, timely performance would meet the audience's expectations of a meaningful musical form based on a common set of cultural norms. The piece would be expected to conclude within a certain time period. It might include an introduction of material, followed by development, and conclude with some kind of recapitulation of ideas. The piece would include novelties in the form of regular intervals, etc. In short, the programmer would be expected to change the program regularly in order to successfully construct a meaningful performance, where meaning within this context is a cultural phenomenon arising from social place, not merely physical space. There are then these sort of two temporal concerns demanded of a cyber-physical programming system. There is a requirement that the system provide a language interface that supports the programmer's desire to orchestrate computational processes in real time, in other words, higher level computational support, whilst also at the same time the system must be capable of realising the programmer's source code intentions into real-time computational processes, capable of meeting the physical demands of the task domain. This is the low-level computational support. A general-purpose programming environment for cyber-physical programming must support both the timely orchestration of computational processes through a programming language interface, as well as the strict real-time computational demands necessary to interface correctly to the physical environment. In the case of live coding, to the sonic physical environment. In order to realise this high level of performance and flexibility on modern multi-core architectures, low-level access to the machine is as important today as it has ever been. High-performance audio-visual code is highly parallel, multi-core, vectorized, SIMD, memory-aware, NUMA, and often makes extensive use of extended CPU instructions on heterogeneous architectures, x86, ARM, PHY, GPU, DSP, etc. Live coding presents a challenging scenario for cyber-physical programming systems developers. Not only must the system provide the high numerical performance and physical sensor actuator connectivity required by modern real-time audio-visual applications, it must also manage these real-time demands whilst providing the human programmer with on-the-fly access to the toolchain, compiler, linker, debugger. Ultimately, the tools of cyber-physical programming must meet the real-time constraints demanded by firm real-time systems, not just in the domain of audio and motion graphics, but across a broad spectrum of domains from server networks to robotics to machine learning, data mining, to high-performance computing and interactive display technologies. This is the broader context of cyber-physical programming. Did you get all that? Look. At the end of the day, really, cyber-physical programming is essentially just REPL programming of a real-time system. And of course, the slightly interesting thing, or the more interesting thing about cyber-physical programming as a programming practice is that it's not just programming a real-time system, but it's programming a real-time system in real time. It's the development of the real-time system in real time. And of course, once that happens, once the programming is happening in real time, the programmer starts becoming part of the real-time system, embodied in the real-time system, and can contribute to the function of the real-time system. So then it becomes the programmer working with the software and the programming language and also the environment, because very often in a cyber-physical programming situation, the environment is part of the state of the program. If we think about the music case, for example, the sound of the music that's being performed in a particular acoustic space, so in a concert hall, for example, those sounds are pinging around the room, and the programmer is not only programming the music, which of course they are doing, but they're also listening to the sounds of the environment and making modifications to the sounds that their program is making while listening to the environment. The program itself may also be listening. It may be that the programmer is also writing machine listening code that's also part of this cyber-physical loop. And so it becomes quite an interesting and complicated loop. There's loops in loops, but ultimately the idea of cyber-physical programming is that the programmer is, yes, acting within the loop, but also to a degree acting as a meta level within the loop, essentially orchestrating these sort of lower level cyber-physical processes that are running on the system. It's important also to recognize that cyber-physical programming very often is ephemeral in nature, to the extent that, code that was written at the very beginning of the session is probably not there at all at the end of the session, or if it is there, it's probably been rewritten 3 times and it's in a completely different form than what it was in at the beginning of the session. This sort of encourages code as an exploratory tool, a way to learn about the world and to explore the world. And it also encourages a kind of a focus on code, not necessarily as a means of production. So we're very focused as a society as code being a means of production, but it can also be an extremely important vehicle for learning and discovery. Of course, there's clearly a corollary here with the work of Seymour Papert and Logo, and work that's continued on with the lifelong kindergarten, and of course has a rich heritage in the Lisp community. In fact, one of my favourite quotes is by Eric Sanderwell, who writes that the average Lisp user writes a program as a programming experiment, i.e. in order to develop the understanding of some task, rather than in expectation of production use of the program. Of course, written in 1978. Ultimately, cyber-physical programming riffs on many of these ideas, extending them onto modern hardware, targeting real-time systems that just weren't possible in the past. In particular, today we've looked at audio real-time signal processing systems, which is actually quite still a challenging domain actually for real-time systems development. We've also looked at computer graphics, physics simulation, and a couple of different examples of robotic control, which of course is a kind of a classic example of in the cyber-physical systems space. Ultimately, I hope that this talk has helped you to think about programming in maybe a slightly different way to the way you have in the past. I know as Lisp programmers, many of you are used to programming in this very exploratory way, and of course that's one of the wonderful things about this community. But I also would like you to think a little bit more about real-time systems and about the programmer's potential engagement in how they might interact in a real-time situation in a real-time cyber-physical system. I'm going to finish the talk early with the hopes that we can head over to the chat section, and hopefully there will be some questions. Again, thank you very much for having me. I hope you've really enjoyed the talk, and looking forward to enjoying the rest of the conference. Cheers.